In this chapter, we look at non-homogeneous problems. So something where there's either a source term in the PDE or a source term in the boundary conditions. So something non-zero. And basically, the idea that the different strategies that we'll see mostly amount to using linearity in a nice way to split apart or redefine the PDE in a way that can move the non-homogeneity from one place to another. So we'll look at things that we can do to separate PDE non-homogeneity from boundary condition non-homogeneity, and so forth. So for the first idea, consider that if you have a linear equation, then the general form for the solution, so this is going back to your ODE class, looks like a homogeneous part plus a particular part, where if you apply the operator to the homogeneous one, you just get 0, and when you apply it to the particular part, you get the forcing term that you want. And so in general, any solution to this equation is going to look like some particular solution plus, and then your homogeneous solution right here is typically the one that would have your arbitrary constants to be determined in an ODE class. Okay, so we can take this this problem right here and split it into two problems. So we're going to consider u to be some v plus y that solve different parts. So we'll take the problem vt minus kvxx equals 0. So we're going to homogenize the PDE in this one. And this is on the same interval and everything. And then VAT is still going to be alpha, and VBT is still going to be beta, and we'll still have the initial condition Vx0 being equal to Gx. Okay, so on the one hand we have, there's our problem for V. And then we will also have a problem for y. So it's got the same PDE, yt minus kyxx, and we'll keep the non-homogeneity, the source term, over here. But then we will have the boundary conditions being both equal to 0 in this one. And then we will also have the initial condition being equal to 0 in this one. And so if we have v that solves the first one and y that solves the second one, then the solution to these two will solve the original problem. And that just happens by homogeneity. So look what happens if I take this v plus y and I punch it into the PDE, then the v part just vanishes, the y part drops out the f that I need to satisfy right here. If I look at the boundary conditions, when I evaluate v plus y at x equals a, this gives me an alpha, that gives me a 0, so together I get an alpha, etc. Right? So the things just add back together. So I'm just using the fact that this is a linear equation to split it apart into two things. And then, so the first one, we already know how to solve. We've seen examples for that. For the second one, what do we do? Well, we can use Duhamel's principle, just like we did in the unbounded domain case. So y is going to look like the integral from 0 to t w of xt minus tau tau d tau, and the system that w solves is wt minus kwx equals 0. So the homogeneous one, but started with fresh boundary conditions at every moment in time. So we've still got the homogeneous boundary conditions, but now we use the non-homogeneity to tell when this thing, or what this thing starts with. So we take a family parameterized by tau, and for each value of the parameter, we start it with the given non-homogeneous condition. So the method of solution is you solve for W first, and then you integrate, just like we saw previously. So this is good for evolution problems. And like initial value problems, right, where we've got the unbounded t variable. It's not so good for equilibrium problems like Laplace's equation. So we'll look at a couple other ideas for how to deal with that.